In this video, we're going to extend our understanding of area under curves, like this area and this area, to finding the area between two curves. So if I wanted to find the area between the blue curve here and the green curve here, what I can do is I can use the fact that underneath the green curve is all fully coloured in, so it comes all the way down. And underneath the blue curve is also all fully coloured in an integral, so it comes all the way down. So if I take this blue section away from this green section, I'll end up with the area in between the two. And so the area between curves is the integral between the 2 points where the curves are crossing, so our two intersection points here and here. And it always needs to be the top curve minus the bottom curve. So we wouldn't write this as top curve minus bottom curve. We would have the formula for the top curve here minus the formula for the bottom curve. So that area of finding the area using the top curve minus the bottom curve, like I've got here, works well when both of the curves are above the x-axis, but it also works regardless of where the curves are located on the Cartesian plane. So we've looked at both of the curves in the top half of the Cartesian plane. So let's have a look at what happens when you have one curve in the top half, like the yellow x squared there, and the other curve is in the bottom half, like that green negative x squared. So let's have a look at how our formula works. So this yellow area here, so we're doing the area between 0 and whatever point this is between the two curves. So the area is made up of this yellow section, which will be a positive area, and we can integrate underneath the yellow curve to find the yellow area. And it's also, the second part of it is this green area, which we can find by integrating between the two endpoints, our green function. So I said the formula always works. So area equals the integral of top curve minus bottom curve dx. So from the top curve, we're going to get a positive area. And then we're going to take away, because there's a takeaway in here, the area for the bottom curve, which is a negative area. Now these two areas just happen to be the same, so I'm going to just label them both as capital A. So this will be a positive capital A and this will be a negative capital A. So our positive area is positive capital A. We're going to take away our negative area, which is negative capital A. And when we combine these two signs together, what you get is positive area, the yellow positive area, plus the green positive area, which is what we want. So our formula, that is the area is equal to the integral of the top curve minus the bottom curve, works when you have one function in the top half of the Cartesian plane above the x-axis somewhere and one down below. What if they're both in the bottom half of the Cartesian plane? What happens then? So let's have a look at this. So if they're both below the x-axis, so here we have here's our x-axis and our y-axis, and here's a yellow curve and here's our green curve, and we're going to integrate between the points where these two intersect. So what happens when both are below the x-axis? Well, let's start with our formula that I've already said always works. So our top curve is our yellow curve here, because it's literally higher up than the green one. That's how you tell top from bottom. Which one is closer to the top of your page, if you like, or the top of the textbook. And the bottom one is the one that's closer to the bottom of the page or the bottom of the textbook. So formula is area is the integral of the top minus the bottom. So the top curve is going to give us this particular area here. Whoops, let me just undo that. I moved that. is going to give us this area here. So that if we integrate the top curve, we get this yellow area here. And if we integrate the bottom curve, we get that whole green area there. And you can already see, if we started with this green area and we took away this yellow area, we'd end up with the white area over here that we're looking for. So that's logical, but let's follow through using this particular formula just to show you that it works. Okay, so the yellow area I'm going to call a small negative area. And then you've got to take away the bottom curve, the integral of the bottom curve, which is a larger negative area. And so you can see where this is going, can't you? So we're going to do a negative small number, negative small value, minus negative large value. These two will combine together to give us negative small plus large, and then I can rewrite this swapping these two terms with their signs. So the plus large comes to the front, minus small goes to the back, and you have large area minus small area, which is what we wanted to do when we looked up here and said if we start with that green area and we take away that yellow area, we'll get the white area in the middle. And when you have a large number and you take away a smaller number, what you get is a positive area. So it works. Regardless of where they are on the Cartesian plane, where the two lines are, it's always top minus bottom, which is handy because that's how you integrate, isn't it? If you've got the integral from a to b of f of x dx, and you substitute into your f of x, capital F of x, you substitute in top minus bottom. Nice. So then the question becomes, which curve is the top curve? And so to figure out which curve is the top curve, you need to know the shape of the function. So you either need to know it from your work with functions at the start of the year, or you can sketch it on your CAS to have a look. And then the other thing you need to know is you need to find the intersection points of the functions, of the two functions. So you can see here I've got two functions, a pink f of x and a grey g of x. And sometimes the pink function is the top function, like here, and the grey function is the lower function. Sometimes the grey function is the top function and the pink function is the bottom function. So anytime they intersect, they're going to swap which one is top and bottom. So you need to find the intersection points. So to do that, what you do is you let the formula for one curve equal to the formula for the other curve, and then solve that equation for x. The x values that you get will be the terminal values. They'll be these values of the x coordinates of the intersection point, but they'll also be your terminal values where you're going to integrate. So once you've found your intersection points, then you need to set your integrals up for each particular section. And so for the first section, what we need to do is we need to say for this section here, we're integrating between a and b, and our pink function is the top minus our grey function, which is the bottom. So you can see it's probably going to be handy to have a highlighter with you in the exam or in a SAC so that you can follow which one is the top and which one is the bottom, because the pictures you're going to get are not colour-coded. They'll both be grey lines and you'll need to figure out which one is which. Sometimes they'll be nice and one will be a solid line and one will be a dashed line, but most of the time they're not. So we've worked out this section here, this yellow section. We need to do a to b f of x minus g of x. Then we need to add this next area here. So this green area here is given by this little section here. Let me just put the yellow section there. And finally, we're integrating, and our integral is going to finish at d. So it doesn't have to always finish at an intersection point, but you do need to have a terminal point of D. And again, in this section, our pink one is our top and our grey one is the bottom. So we find each of those areas individually and then add them all together. So let's look at an example of a question. So here's the example. Find the exact area bound by the curves y equals negative x squared plus 3, so an inverted parabola, and y is equal to 1, so a horizontal line. So the very first thing I did there was I told you what these curves look like. So that's what you need to do first. The very first step in solving this thing is to determine what does it look like. And so it looks like that, with our y equals minus x squared plus 3, our inverted parabola, and our second equation y is equal to 1. And so the area that we're looking for is bound by those curves. So it's going to have its outside as one function and the other side as the other function. So what we're actually looking for is this little bit in here. And so to do that, we're going to use our formula for the area between two curves, which is the integral of the top curve minus the bottom curve. But before we can do that, we actually have to find out what these intersection points are here. And so we're going to need to make our two equations equal to each other. So we're going to find this value and we're going to find this value here. One's positive, one's negative. The parabola is symmetric, so whatever value this is going to be the negative version of it. So that way we can double check we've got our answers right. So to find the two intersection points, what you do is you let the two equations equal to each other. So I've taken the first equation, y equals minus x squared plus 3, and I've made it equal to the second equation, which is 1. I've given myself a very easy one to do. And so minus 3 from both sides, multiply both sides by minus 1, x squared is equal to 2, so x is equal to plus or minus root 2. So I can put that on my graph. So now I need to integrate to find my area. And so the area is equal to the integral from our lower terminal, minus root 2, to our upper terminal, root 2, and it is top curve, which is the white curve, so the white formula goes first, minus x squared plus 3, and then take away our bottom curve here. And so what we do next is we find the antiderivative by anti-differentiating these terms here. So we get negative x cubed on 3 plus 2x, and then we're going to substitute in our root 2 and our minus root 2. So let's go ahead and do that. And what you get looks like that. So we've got negative, and then the x, which is our square root of 2 cubed. So when we substitute in our negative root 2, we've actually got a negative, and then we're substituting in our negative root 2. And making sure that we watch out for those things, our positives and our negatives as we go. And so now we're going to need to go and do some simplification. And so we're going to need to break out our knowledge of root 2 cubed. So root 2 times root 2 times root 2, those two can combine together to give you 2. So the answer is 2 root 2. So you can see that my negative stays out the front. The square root of 2 cubed is 2 root 2. And I've also got negative of the negative square root of 2 cubed. So the negative square root of 2 is negative root 2 times negative root 2 times negative root 2. these negative times a negative times a negative gives you a negative overall, and so it simplifies to negative 2 root 2, which is what I've done here. And then I've gone through and I've multiplied this negative sign, this takeaway, all the way through. And so you end up with negative 2 root 2 on 3 plus 2 root 2 minus 2 root 2 on 3 plus 2 root 2. And so again, we go through and we gather our like terms together. So I added 2 root 2 plus another 2 root 2 to give me 4 root 2. And then I had minus 2 root 2 on 3 minus another 2 root 2 on 3 gives me minus 4 root 2 on 3. And that finally gives me my answer. So I write both fractions, both as fractions with the same denominator by multiplying this by 3 on the top, and there's a divide by 1, 3 on the bottom. So it gives me 12 root 2 on 3, which gives me 8 root 2 on 3. So if you were doing this as a CAS calculator question, you would obviously graph it and find the area that way. I'll show you that in just a minute. In fact, I'm going to show you how to do it now. So put your two functions on your graphs page, and then go menu, analyze graph, and choose bound area. Now, if there's two curves on there and there is only one contained section, it should automatically it should automatically select the section. But you can see here there's different sections where these curves overlap. So you'll need to put a lower bound in. And to do that, you just bring your mouse over and click on the intersection point and select it, and then just move across to the other terminal point and click, and the area of the shaded region will appear on your screen inside the grey area there. Right, now let's have a look at an interesting question. So I really like this question because it really makes you think. The area of the shaded region is given by, so here's our area of our shaded region. So if we wanted to write it as a whole integral, it would be the integral from A to C. Our top function is g of x minus our bottom function, which is going to be the other one, obviously, which is going to be this one, minus f of x dx. But when you look at the answers, can you find that anywhere? Okay, it's not there. So we're going to describe this particular area here in a different way. And I'd really like you to pause the video now and have a go at copying this little layout onto your notes and then shading in the areas that each of these integrals describe, and then seeing what you get from there. So to show you what I mean, I'll just go this way. I've done A for you. So A says the integral from A to B of g of x. So A to B of g of x gives you that green area there. And already you can see we're missing a little bit here. Then it says plus the integral from B to C of f of x, which is going to give us that yellow area there. And that's not right either. So there you go, have a go at the others. Press pause, and when you think you've got an answer, come back and see what I've got to say. Okay, well, we already know it's not A, and it's not B either. It doesn't give us the right. This integral here is kind of okay for the first bit, but our second integral has our bottom minus top. So that's not correct. Our third one, put put those back, has our a lower function, our bottom function, minus our top function. So that's not right. So let's have a look at the other ones. Come on, move up. Let's have a look at these last two. Now hopefully you selected D. If you selected D, you're right. We've got swapped terminals here, and then we've got the lower minus the upper. But if we swap these terminals back around the other way, they'll just become a negative sign, a negative symbol at the front of our integral of our purple minus blue. And this is like a constant minus 1. And so I can bring this back inside and multiply everything in here by -1, which means this will become negative and this will become a positive value. So now I've got the integral from negative f of x plus g of x. And I can take these two terms and swap, bring this plus g of x to the front, move this minus f of x to the back, and we get our proper formula. So if you are trying to find a question, solve a question like this, if you swap your terminals, your area between your two curves will become the integral of bottom minus top. Very interesting. But always remember, this is only if there is some kind of trick question in the multiple choice question like it was before. 99.99% of the time it will always be top minus bottom.